So, like in a Latin America soap opera, we will start by saying what we saw in the last lecture, what happened in the last episode. So, we ended up with this set of equations that was the Maxwell equations. And the Maxwell equations were equations that told us what happens with the electric and magnetic field in the presence of sources that today we will set to 0. And the lecture of today will start by looking at solutions of these equations in vacuum, meaning you are in outer space, there is no charges, we want to know what happens with the electric and magnetic field, okay? And the four Maxwell equations are the equations that I just wrote down, and we define this speed, 1 over c squared, in terms of epsilon 0 and mu 0, that were two constants that appear in Maxwell equations. And there are different vector operations. So there is the divergence, gradient, and curl that are defined like this. Okay? Any questions about this? Beautiful. So today we will look at solutions to these equations. So these E and B are functions of space and time, and we want to find solutions to those equations. In order to do this, we will use the following vector identity. I'm sorry that there are many vector identities in this business, but if you do the curl of a vector E, any vector, so this is a vector identity. This we can write as the gradient of the divergence minus the Laplacian acting on this. Remember, the Laplacian acting on something is the second derivative of x plus the second derivative of y plus the second derivative of z as an operator. And now, so this is true for any operator, but now we will use the Maxwell equation, and the Maxwell equation 1 tells us that the divergence of E is equal to 0, okay? So we don't have this term, and then this is minus the Laplacian acting on E, okay? And this is using here the Maxwell equation 1. So this is a vector identity for any vector, and this is the Maxwell equation 1. On the other hand, we can write down the same object by using the Maxwell equation 3, and the Maxwell equation 3 tells us that the curl of A is related to the derivative of B, so this is minus the curl of dv dt. We exchange time and curl derivatives because they commute. And now we use equation 4 to write the curl of B in terms of this derivative of E with respect to t. Okay? And from this, we deduce that this is minus 1 over c squared, d squared E to dt squared. Beautiful. So, just by using the Maxwell equation and that vector identity over there, we have proven that the Laplacian acting on E minus 1 over c squared, the second derivative of E with respect to t is equal to 0. Beautiful equation for the electric field. All right? Any questions about this? This is just a beautiful consequence of the Maxwell equations and that vector identity. Okay? You can believe me that if you do the same kind of tricks, you can also prove that the Laplacian of B minus 1 over c squared, this we are not going to prove, but you can prove it as an exercise. It's not a particularly hard exercise, but it is true that you can also show this. Okay? So these equations, or this equation in general, you have already seen it in Fourier, for instance, in the first year. It's nothing but the wave equation. Okay? So these sort of equations, okay, here we are in 3 dimensions, but they are called the wave equations. And we will look at a scalar case. Okay, so this f, imagine that we have a function f instead of a vector f. We have a function, and the function satisfies this. We will start by looking at solutions to this equation. Okay? Sorry, not vector. So these two are wave equations, and we want to learn, we want to see how do we find solutions to this wave equation, okay? To these wave equations. So let's try first with this scalar case, just the case where f is just a function, it's not a vector, it's just one component. So the first thing we can try, and you have seen this in Fourier already in 1 dimensions, is we try f equals a function of k dot r minus omega t, okay? So here r is the usual xyz position vector. K is a constant, and omega is also a constant. You take this, baby, you put it up in f, you take derivatives, and you see that actually it works perfectly. So it is a solution provided the following is true: omega squared is equal to c squared, the absolute value of k squared. Okay? So whatever function of kr minus omega t you put into the wave equation, it works, provided this relation between omega and k work fine. Now, notice that, so these solutions, they are called plane waves. And the reason that they are called plane waves is because f is constant on a surface in which k dot r minus omega t is equal to a constant, simply because f depends only on this combination. It depends on r and t through this combination. Okay? Now, if t is constant, imagine that t is fixed. So for t fixed, this one here, in terms of r, is the equation of a plane. You may remember that in geometry, k dot r equals a constant. That's the equation of a plane. Okay? So this geometrically is a plane which is perpendicular to k. Okay? So this is the equation of a plane. And now, as t increases, this plane moves in the direction of k. Okay? So the plane at which this is constant, let's say equals to 3 or whatever, moves in the direction of k at the speed c. All right? Which is omega over k. So as t increases, the plane on which f is constant moves. And it moves in the direction of k at speed c. Is that okay? Yeah? Any questions? Comments? Complaints? Super. There is a even more cool way to see this, and now it should be super explicit. So there is a specific kind of solutions, which is a function of kr minus omega t, in which we choose f of kr minus omega t equals a sine or a cosine of kr minus omega t. If you are grown-ups, you write sines and cosines like this. Okay? So that if you take the real and imaginary part, you get the cosine of kr minus omega t and the sine of kr minus omega t. But it's much better to combine them into this. And this is called a monochromatic wave of frequency omega. Okay? Is that all right?
So are we just taking the specific function into the I that?
That's correct. So we are taking a specific function, and so we can take any function, right? We could have taken the tangent hyperbolic. We could have taken e to the e to the e to the e to this, and the differential equation still works. So the differential equation, very much like for the wave function in Fourier, the differential equation works, okay, for any function of kr minus omega t. The beautiful thing about this specific solution is that, as we will see in a bit, it will correspond to light of a specific color. Okay? So when you have a wave of light, you will have this form. And Fourier tells you that actually any function you can decompose into this sort of solution. So any solution you can write down as a linear combination of this. Okay? But the reason why this is powerful is because light, blue light, it corresponds to that, to these sort of things. Okay? Any other questions? Beautiful. You do the same with the wave equation in Fourier. Like, yeah. Very nice. So now, based on this intuition, we propose for the electric and magnetic field the following forms. We say that E is equal to a unit vector, E, times some magnitude, E to the I kr minus omega t, and B is B times B0 E to the I kr minus omega t. Okay? And here, E and B are constant unit vectors. E0 and B0 are also constants, and they measure the magnitudes of E and B, and K and omega are also constants, and they will be measured in the direction of the wave, and omega the frequency of the wave. Okay? So K direction and omega frequency. Beautiful. So now all we need to do is we need to take these two. Do you know how to use Mathematica? Or some software like this? So you basically take these two things and plug them into the Maxwell equations. And that's it. And actually, this e to the ikx, etc., will always factor out, and you will get conditions for this E, B, K, etc. Okay? So all we do now, we take these two ansatz, let's say, based, of course, the ansatz based on these two equations that we got before, and now we plug them into the Maxwell equations. Okay? Notice that these two are necessary for the Maxwell equations, but they are not sufficient necessarily because they are only two equations. But just to be sure, we take these two and we plug them into the four Maxwell equations. Okay? So for instance, if you just take the first two and you just plug E and B into 1 and 2, so you have the divergence equals 0, for instance, the divergence of E equals the divergence of B equals 0, they imply that E dot K and B dot K have to be equal to 0. Okay? So what this means, what these equations mean are that E and B are perpendicular to the direction of propagation. Which is K. The other two equations, so we get these two conditions. Now we have the other two, this and this. If you take these two and plug them into the Maxwell equations, we get the following. Which looks a bit complicated, but I will tell you what the conclusions are. So we get K wedge E is 0 minus omega B0 equals 0, and K wedge B0 plus 1 over c squared E is 0 equals 0. And these two together, they imply, first, they imply that c squared K squared is equal to omega squared. And that's cool. It's the condition that we already knew from solving the wave equation. Okay? But also, we get that E and B are perpendicular. Indeed, for instance, from here, you can see that B is the wedge product of K with E. But you know that if you have a vector, the wedge product of this with this is always perpendicular to both K and E. Okay? It's like if you have a vector A and a vector b, the wedge product always points in the perpendicular direction to both of them. Okay? So ijk, for instance, two are the wedge product. Sorry, one is always the wedge product of the other two. And in addition, B0 is 1 over C E0. So the magnitude of the electric and magnetic field are related by the inverse of the propagation of the speed. Okay? Beautiful. So now it comes something quite cool. So what is the shape of all this? So what we are saying, if this is k, the direction of propagation, then E and B are perpendicular to k and perpendicular to each other. Okay? So, for instance, if B points in this direction, E has to point in this direction. So, this is the way that the electric and magnetic field propagate. Okay? So, it's like imagine waves going up and down, and the waves propagate in this direction. So basically, we have the electric field that oscillates in this direction, the magnetic field oscillates in this direction, and everything moves in this direction here. Is that okay? So this is the conclusion of our equations. Now, these solutions are nothing but light. Okay? And if you go to your electric circuits and you measure epsilon 0 by completely independent means to all this, and you measure mu 0, again, just by doing some magnetic experiments that we probably all did when we were like 12 or 13, then we can put them together and see which C do we get, and we get C equals 3 times 10 to the 8 meters per second, okay? Which is precisely the speed of light, all right? Now, this, first of all, people was extremely excited. Newton and people after Newton, they have derived a lot of equations of optics and a lot of properties of optics. And it turns out that from these properties, from the properties of our solutions, you can prove, kind of from the Maxwell equations, all these laws of optics, that from optics it looks obscure, right? Do you know, for instance, that when you have a mirror, you reflect light, and the light comes out always at the angle at which it reflects? You can prove this from these equations. You can prove a lot of things, like every law of optics that you can think of, you can prove it from these equations. So this was one of the biggest triumphs of the 1800s, okay? The fact that we can now predict light, predict the speed of light, predict the properties of light from equations that just followed from electric and electromagnetic circuits, right? How cool is that? Any questions? Before we get sad, but now we are happy. But do you have any questions for me? Yes.
So it makes sense mathematically to focus on the exponentials as a primitive kind of solution, but let's say you're an early physicist, whatever, 5 years after Maxwell, and for whatever reason you're the first person to do that.
Yeah.
What makes you then go, oh yeah, this primitive solution, yeah, that's like whatever.
Yeah.
So that's slightly missing here.
Yeah, absolutely, 100%. So okay. So first of all, the question is a really good question. But 5 years after Maxwell, it was the first time that physicists met this equation, but not the first time they met waves. Waves, they have been discussing by decades by then. But they have different kind of waves. And when you have different kind of waves, it makes sense, even in a swimming pool, to talk about waves of a definite frequency. Okay? And waves of a definite frequency, they found it convenient to have sines and cosines. Okay? So, and sines and cosines, basically, you combine into these exponentials. So, they had a lot of experience with waves, actually, a bit too much experience with waves. Because there is a crucial difference, and now I will tell you. Thank you for the question, actually. That's an amazing question. So when you have a medium, and you have a sound wave, or any kind of wave, up to this point, every single kind of wave that physicists had encountered, amazing question, by the way, thank you. It was a wave somewhere, in a medium, okay? So the medium, imagine you have gelatin, right? It vibrates somehow. And this vibration propagated, okay? And physicists could not understand that the lights, the waves of lights, propagated in vacuum. There had to be something, okay? Like when I talk to you, the particles of air go in this direction, right? And this is what propagates. And if you have seen any movie ever in space, when you hear sound in space, that's not true, okay? So like when you are in Star Wars and something explodes, you don't see that, you don't listen to that, because there is no medium for sound to propagate, okay? So you would die without listening to it if a spaceship explodes next to you, all right? Because sounds needs a medium to propagate. And physicists, they thought, okay, maybe there is a medium and light propagates in this medium, but the medium is so weak that we cannot detect with any other means, okay? And that is what they call the ether. So indeed, they knew waves very well, but every wave they have met so far needed a medium to propagate. And then everything followed. Like then it was just like any other wave, okay? So there is a few questions that are burning, and we will answer them today and tomorrow. So the first question, so we are assuming that we need a medium. The medium was the ether, according to them. It was a medium that filled the whole universe in which light propagate. We will kill it soon enough, but for now believe that there is some ether. And then, with respect to this ether, the speed is c. Because remember that I told you, we discussed the last week, that you cannot talk about velocities in an absolute way, okay? You need to choose your reference system, your inertial frame, and once you have chosen your inertial frame, you can measure the speed of things, the velocities of things. However, if someone else chooses a different frame, they will measure a different speed for the same objects, okay? Because the two frames would be moving with respect to each other. On the other hand, the Maxwell equations tell us, no, the speed of light is c, and c is this number, always this number, okay? So what they thought is, okay, there must be a system which is at rest. This system is the ether, and with respect to that system, the speed is this speed c, okay? And that is what people thought. That is what people thought it was the point. Another thing that I will tell you before we proceed is that sometimes we will find it convenient to talk about particles of light, and these particles of light are called photons. So for now, you need to think of a photon for now and for the next 2, 3 years of your life, think of a photon as a particle that moves at the speed c, okay? And we will use one small result of quantum mechanics, and we will come back to that later. And the result is that the energy of this photon is a constant times the frequency of light. Okay, this is a result we borrow from quantum mechanics. So this is a very tiny number. It's called the Planck constant, h bar. We all call it h bar. This is the frequency of light, and we think of light made out of photons. Okay, and photons will be these particles that move at the speed of light. All right, very nice. Any questions? Great. Now, people, because the speed of light is incredibly fast, light is really fast, it is very hard to say whether if you move with respect to light, the light will appear slower or faster to you, okay? Because the speed of light is so much, is 3, is this number here, is so large that it is hard to measure that, and especially it's hard to measure differences, okay? Like, let's say I start running, and I run, of course, this is much slower than 3 times 10 to the 8 meters per second. I will not see any difference, okay? So, however, the Earth is moving in the universe, all right? The Earth is oscillating around the sun. So if ether is at rest with respect to the sun, we should see a difference if we measure light moving in the direction Earth is moving or the opposite one, okay? This is still very hard, but we got very good at measuring, and we got so good that someone called, 2 people actually, Michelson and Morley, and this is not the tensor product of the 2, it's just wanted to measure the velocity of Earth in the ether, okay? So what they did, their experiment was the following, very, very smart experiment. Imagine that using light here, imagine first that you are at rest with respect to the ether, okay? And you send light, and you split it into a mirror, and you send 2 lights. A red beam goes, reflects back, and this distance is L. And the second one goes like this and goes back, also a distance L. And here is the reflecting mirror, okay? So basically, you send a beam of light in that direction. The light reflects a mirror at a distance L and comes back, and the other one in that direction, okay? And the light does the same. So if we have this is light, it's not a vector L, light. If we do this, then the time that light takes to do the blue path is simply distance 2L divided the speed of light, okay? And the time that the red beam takes to go up and down is also 2L over C, okay? So this is fair enough, easy enough, and I hope we all agree. Now let's make it more interesting, okay? Let's imagine, so this is the first thing. Let's imagine now that the experiment or that we are move at speed v in the blue direction. Okay? So now the picture is as follows. The origin is somewhere here. Okay? This is the distance L. But because the ether is moving at the speed v, okay? Sorry, so we move at the speed v with respect to the ether, then the mirror is moving to the right, and then light has to hit it like here, and then come back to the point origin that has moved. Okay? So basically, imagine I have to hit you, let's say, so not personal, okay? But you are running in that direction, then I need to aim like this, okay? And then the path that my light, harmless enough, will do is a bit longer, okay? So if you compute, we will compute that in a second, but you can see that the red path has to do this now, okay? And the blue path is also a bit different, because when you throw light into that direction, the target is moving away from us, okay? So that the target will be somewhere here, let's say. So light has to do this, hit the target, and then come back to the reflector O, to the receiver O, okay? So the red light does something which I just showed, and the blue light does this, okay? Let's compute both now, both times. So, good. So here, in this situation, notice that T red is the same as T blue. Here, let's start with the time blue. Now, when light goes towards the target, like this, towards the reflecting mirror, because the mirror is running from us at the speed v, the velocity is effectively c minus v, okay? It's like we are moving a bit slower. We are reaching the mirror in a slower way. However, when we come back, this is actually called interferometer. The interferometer is moving towards us, okay? So that effectively, the speed is c plus the speed of light, okay? So the time that the blue ray takes to go back and forth is this time here, okay? Because when it goes towards the target, it is a bit harder, so it's like our speed is slower. But when we come back, our speed is faster. Do you agree? Yeah? So this is this one here. On the other hand, T red can also be computed as follows. There is a super nice way to compute T red actually, and it's the following. Sorry, I will do the red computation in red. 1/2 T red, the time light takes to hit the mirror. Okay? Red light. So the time that light takes to get from here to this mirror here. Okay? Now, in this time, 1/2 t red, the mirror has moved, okay? And how much it has moved? In this time, the mirror moved v times the time, which we are calling it v over 2t red, okay? Then, by Pythagoras, we just get the following equation. The distance traveled by light, then, is L squared, but we need to add the distance that the mirror has moved to the right, which is v squared over 4 t red squared, okay? But remember, by definition, the light makes twice that distance, okay? So because the light has to go back and forth, all right? So that by definition, t red is the total distance, which is 2d divided by the speed of light, c, okay? But d, we just got it from here. So this is 2 over c square root L squared plus v squared over 4 t red, which is super cool because we now got a beautiful quadratic equation for t red, okay? So it's a very nice way to do the computation. So from here, we deduced, and you can show that t red is 2L over c squared minus v squared. And here comes the beautiful thing. Now, this t red, let me go back to blue. Now t blue and t red are actually different. And the difference for small velocities is something like this, okay? So this is for small velocities. Now, Michelson and Morley have the following idea. So they send the lights towards the red mirror and the blue mirror. The beams of light would hit the mirror, would come back, and then they had an interferometer in their experiment, and this interferometer could measure whether the two waves were in phase or off phase, okay? If they were on phase, then it meant that the time they took was the same time. If they were off phase, it meant the time was different, okay? And furthermore, what they did was they did the experiment. They basically didn't see any difference, and then they started rotating the experiment. Now, when you rotate the experiment, the roles of blue and red get exchanged, okay? And you should see a sign here. You could say, how do you know that the length of this arm is the same as the length of that arm, okay? And that's very hard to measure. But their bright idea was that if they rotated, no matter how small mistakes they could do in these lengths, you should see a difference, okay? Because if you move in favor or against the ether, you should see that the speed of light changes. And what they call refraction pattern should also change. However, they found the following negative experiment, and this is one of the most famous experiments in history of humankind. And the observation is that in all inertial frames, the speed of light in vacuum is a constant independent of the direction of propagation and the speed of the source. Okay? This contradicts all our intuitions from Galileo, Einstein, up to that point, how in all inertial frames there is one speed that is constant. And imagine, right? Like you are really accelerating and you throw light, you will measure that light. Like you are going really fast, you throw light, you will measure the speed c. Someone who is standing and sees you doing that will measure the same speed c. Someone who is coming against you really fast also sees that, okay? I was torturing my son yesterday, telling him that, and he told me, well, surely if you are going to the speed of light, then you will see the photons around you going at the same speed and just in rest. No, even so, you would see that the photons go always at the speed of light, okay? Any questions about this? Beautiful. So we will end up with the following. People was quite shocked by this. And in particular, it was understood that this is actually not consistent with some of the postulates that I wrote in the previous lecture, the postulates of Newtonian mechanics. And because of that, Albert Einstein said, we need to forget about them and we need a new set of postulates, okay? So he wrote the postulates of special relativity, and they are as follows. So there is a preferred class of frames which are simply the inertial frames, okay, and in which the law of inertia follows. And they all move at uniform relative motion. Then he says that inertial frame plus a choice of 0 for t, determine the inertial coordinate system. ICS. And then the two big ones, well, these are huge too, but these were the same as the one we had before. The third postulate is that the laws of physics, any law of physics, all laws of physics, electromagnetism, mechanics, all the laws hold in any inertial frame and the last postulate is the observation we just made, which he elevated to a postulate. In all inertial frames, the speed of light in vacuum is a constant independent of the direction of propagation and the speed of the light source. Okay? Based on these four postulates, he created this special theory of relativity that completely changed our conception of space and time. Okay? Notice that we have to give up a lot of things. We are giving up Galilean transformations and addition of velocities. We are giving up conservation of freaking mass. Okay? So mass is not conserved anymore. But it turns out that if you ask for these four or all the others, you cannot have the cake and eat it, right? So it's these four, okay? And what he understood is that these four are the correct ones. So from tomorrow, we will start building the special theory of relativity based on these four postulates. Okay? Thank you very much, and see you tomorrow.